This is House Planning Help episode 94. Hello, I'm Ben Adam Smith, and this is the podcast for you if you want to tackle a self-build or a remodelling project. I'm exploring what houses we should be building in the 21st century. My personal goal is to create an energy-efficient home before I turn 40 in August 2016. Coming up in this session, my guest is Brian Murphy from Green Building Encyclopedia, and we're going to be looking at 10 insulation types and why you might want to specify them. It's a fairly long interview, around about 30 minutes, so I'm not going to hang about today. We'll just get stuck in. The topic, again, is insulation, and if this were a money podcast, then it would be a bit like talking about tax. It's a topic we know is important. We're probably not going to be doing this ourselves. The specification might be the architect or someone else in the team doing this. But what I'm hoping is that we'll just get a gist for an area that has so many variables. I started by asking Brian to tell me a little bit about his background.
I'm an architect by training, a specification writer by choice, which I did for about 15 years. And I've been in the industry for 40 years. I've specified £2,400 million worth of work, predominantly larger projects, but I'm more interested in smaller, greener projects these days, so that's where I'm putting all of my efforts.
What do you mean exactly by specify?
Well, it's like writing a recipe for a building. You have to describe every component, every material, how it's used, what the mixtures, how do you apply them, what tolerances and surface finishes you're looking for, so that there is absolutely no doubt for anybody, including the people who price them, the people who build them, the people who buy the materials, everyone has to know what's required so that there's no doubt, and you write it once and there shouldn't ever be another question.
And in your time when you were doing different specifications, presumably you were learning too. Were there any surprises?
Yeah, when my first freelance commission was the New British Library, which was a bit of a challenge, £500 million first go. I was given a part-time post there for 14 hours a week. And it took me 3 months to realise that when we are used to writing, doing drawings, a single line is a single line in ink on paper, or in these days in a computer. But as I progressed, I realised that any one line might be 6 or 7 different processes. And so it became quite daunting to do specification as thoroughly as I've had to. But it's a great way to learn how to do things and get better at what you do.
We're talking insulations today, and we're going to look at 10 specifically. Will there be lots of others that we don't mention, or has this really got them in this list?
This is the bulk of things. There probably are 1 or 2 other materials that there's combinations and there's different mixtures of things. There's been a lot of playing around with blending of chemicals in making different kinds of plastics. I'm only going to talk about plastics as a single group. I'm not going to break them down into the many different plastics that are used in different applications, because I kind of lump them together, and I shouldn't. I know that, but that's the nature of the game.
Do all insulations do the same thing if there's enough quantity of them?
No, it's interesting that we're in the habit, and the building regs drives us in most respects. We're focused on conductivity and thermal resistance and U values, the kind of total calculation for an external wall or a roof. And that's only one of at least 3, possibly 4 different ways that we need to think about thermal insulation. I put them into groups. There's conductivity insulation, convection insulation, and radiation insulation. And radiation insulation is probably the more important one, because it's the one that we're going to engage with more and more as we progress to a hotter climate closer to Mediterranean climates in the UK.
Can you give that a little bit of an overview of those 3 that you mentioned? And are we trying to get a balance sometimes? Is that why this is changing?
I tend to see them as we're really focusing on one thing most of the time, but in some cases we do have to have more than one characteristic in one place. For example, a pitch roof, which is going to be subjected to the sun, it already is subjected to the sun. That sun, the heat of the sun and the warmth of the day is going to get progressively warmer as we move towards a European Mediterranean climate. The solar gains are going to make rooms and roofs very much hotter. And if we've got a good mixture of radiant thermal insulation protection, stopping the heat getting in, and also some conductivity thermal insulation, then we're going to stop the heat getting out. The risk is that if you let the heat in, and you don't let it back out again, you're going to overheat upper parts of the building. So there is a risk, and we do need to start mixing the two types of insulation for two particular purposes.
Let's start off our list. At the top, we've got glass, rock, mineral insulation. Is this at the top for a particular reason? Is it the most common?
It's usually the lowest price, and therefore it's used by the vast majority of people in the vast majority of locations. And it's a very good conductivity thermal insulation. It doesn't have a lot of decrement delay, the radiant heat thermal insulation. So in a roof, it's the standard material that's used generally, and projects like the Green Deal and other insulating programs that the government have got in place recognise glass wool and rock wool, and unfortunately it's not the right material for most of the places, particularly roofs.
Can you give us an example of what decrement delay means?
Well, what happens is that when the sun beats on the roof gets hot. If you've got a black or blue slate, it's going to get hotter. That slate will then re-radiate the heat inwards into the attic. The attic gets hot, and then, if you've ever been in an attic trying to get stuff out in the middle of summer, it absolutely cooks. It's just unbearably hot. So that heat will find its way into the rest of the building. So it'll go to the bedrooms, the upper floors, soonest, and those upper floors will overheat during the summer. And if you've got a very well-insulated roof with 300 millimetres of insulation of the conductivity type, that heat will stop getting out again. So what you need to try and do is stop the heat getting in the first place to stop it overheating. So then you need the decrement delay.
Getting back to glass and rock mineral insulation, it sounds like there's a lot of manufacturing that's gone into this.
Yeah, if you imagine trying to take a stone and melting it, takes an awful lot of energy. Then they turn it into a fibre by blasting air over it or dripping it and blasting air over it. So lots of energy to go in, but it's one of those manufacturing processes where they're producing millions of square metres of the stuff. They're producing it in the most efficient way imaginable compared with a kind of one-man band making natural materials. So there is a degree of efficiency, but there's still an enormous amount of energy that's gone in.
This may seem very generalised, but because, of course, there's so many situations you might use it, but why might you use it and why might you not use it?
Well, the primary use is for conductivity thermal insulation, so it's going to be used in roof construction, in timber construction, even in cavity wall construction, masonry cavity wall. So it's a fairly versatile material. It can be used for thermal acoustic fire performance. So, but the one characteristic it doesn't have is the decrement delay characteristic. It's got to be very dense in order for it to have that characteristic. So it's not the ideal material for use in roofs. The other important aspect is that it's hydrophobic, which means it will reject water. It doesn't like moisture, but the other natural materials that we're beginning to see a lot more of are hygroscopic, which is a completely different characteristic and one which we need to understand and get to make the most of.
Is there anything else we need to mention before we move on from glass and rock wool mineral insulation?
Well, there are reasonably strong differences between glass and rock. There used to be slag as well, which is a kind of byproduct from steel production, but that doesn't seem to have the same market share that it's had in the past. So glass wool and rock wool, you'd use rock wool where you're looking for a fire performance, and you might use glass wool in an acoustic performance situation. So although both have the characteristics, they don't have the same characteristics.
Number 2 on our list is polystyrene and what you said at the beginning, other plastics.
Yes. The interesting thing is that the plastics do have a range of characteristics. They do have some are there's some products that have been brought into the market recently are recycled plastics, which have a non-itch characteristic. So there's an interest, especially on the self-builder's part, to actually have a material where you don't have to have special suits, special breathing apparatus, so that you don't have the problems of itching afterwards. The plastics that we're more familiar with are the polystyrenes, expanded, extruded, polyurethanes. They all have different characteristics. They all have different gases in them. Some are blown in. Some happen as a part of the kind of expansion process. But the blown in ones tend to have the chemicals that historically were ozone depleting. And as time has gone on and as legislation has driven them, those gases have been changed to more benign gases, but they're still required to make the bubbles which make the material insulating. And it's about trapping air inside those bubbles. Sometimes it's not just air, sometimes it's other gases like carbon dioxide and other chemicals. But trapping air inside plastics stops it from moving and stops the heat from passing through them.
I always think of this one as one that you'd use in the foundations, but again, is it quite versatile?
Yeah, I guess it is quite versatile. Polystyrene is often used under floor slabs. It's also used in cavities underground. It's used in cavities at ground level, and it's used in cavities above ground. So it's versatile in that respect. There's quite a lot of manufacturers who are making polystyrene for pitch roofs, flat roofs, in different situations, some of them with a kind of squeezy characteristic, which means you can apply them into the gap between rafters, let go, and then they'll push outwards and hold themselves in place against the rafter sides.
Why might we specify polystyrene-based insulation?
Interesting one. I guess because they are water resistant, durable. Another application is in an inverted roof situation where you put them above the waterproof membrane and then weigh them down with paving slabs. So they are waterproof in both locations, under the slab and above the roof. And so that's one of the reasons why you would pick that material.
So are there any other applications that we need to look at for polystyrene or plastics?
Yes. You're probably familiar with the term SIPs, structural insulated panels. They use polyurethane usually, between two sheets of OSB usually, sometimes plywood. And OSB is a kind of wafer board which is somewhere between plywood and chipboard. It's a material which has some of the characteristics of both and an economic price in between them. So SIPS panels are structural. You can make whole buildings with them. You can make panels. You can make up panels which are for self-build. You can make up panels which are larger, whole buildings even. You can even have whole pods, modules, half a house, a quarter of a house, an attic, all prefabricated, delivered to site, assembled, craned into place sometimes. And they have a lot of the characteristics that you need in terms of conductivity, thermal insulation, but very little of the radiant protection from solar gains. So I suspect there'll be some SIPS buildings which will be overheating too.
We better get moving on our list, because that's the thing about a list of 10. It takes a little bit of time, but cellulose fibre.
Yeah, so cellulose fibre, it's recycled newspaper turned into flake, so it's shredded and flaked and available in bags, sacks, delivered to site, put into a machine that's then blown into the cavity of timber frame construction normally. So there are two approaches. One is blown in dry, another one is blown in wet. So it's a bit like papier-mâché at the end of the day. It's rigid, it's not going anywhere. There are fears that the cellulose fibre flake blown in dry can settle, but it's about setting the density on the machine so that it makes sure that they're solidly filled cavities. Some are spray applied from an open face onto an open cassette, and sometimes they're blown in through a hole, and that type they will be blown in with a particularly powerful, I think they're called turbojets, where they're blown in and blown into every corner of the cavity so that there's very little risk of heat loss at the edges, where in the alternative situation, if you've got a board material or a quilt or you cut it, fit it, if there's any gaps, you've got the high risk of condensation occurring where those gaps are.
In terms of insulations, as we're looking at this whole list, is there any benefit over a rigid one compared to one like this that's just little bits, and how do the two compare?
Well, usually a rigid material would be applied on the outside face or the inside face of a stud frame construction, whether it's a metal stud, a timber stud, even traditional timber post and beam construction. So you would apply them by applying them on the face, fixing them through the face with a special fastener into the timber construction or the metal construction. So they're designed to span, and then they can carry things like roof tiles, battens, felts.
And this is also a good one in terms of moisture management.
Yes, that's right. We briefly talked earlier about glass wool and rock wool. They're hygroscopic. They hold the moisture in the airspace. Any moisture in an airspace stops the airspace from insulating. When you get to a cellulose fibre, any moisture that gets into the material gets absorbed into the fibre itself, leaving the airspace to do the insulating as it was intended. So it can accommodate a fair amount of moisture in the construction and still perform to its best.
Next up, we've got sheep's wool, which is obviously a nice renewable one, so long as you've got lots of sheep around.
Yes, and of course, one of the great things about the green and the violet industries, as I call them, the two halves of the sector, is that they are always kind of telling you porkies about what's wrong with the other guys. And the one thing that the guys will tell you about with sheep is the methane from the sheep. As sheep eat grass, they poo, they make methane. And of course, the methane has a higher global warming potential than carbon dioxide. And there's even discussions about, do you put devices on them to capture the methane? All kinds of silly stories going around. But the important thing is that sheep's wool itself has some interesting characteristics. It has the normal conductivity characteristic, but it has an interesting one. You think of sheep in the rain, especially in the UK rather than in New Zealand, somewhere like that. Sheep seem to be quite happy wet. And that's because there is a characteristic of the insulation warming up when wet and cooling down when dry. So there's a very strange characteristic, which I don't really understand thoroughly. A friend of mine did a PhD on the subject, and he doesn't like to talk about it because it's not one that people engage with very easily. So, yeah.
Is it a case that with sheep's wool and all of these things, there's not much to do to it, so you're saving in terms of processing as well?
Yeah, there are. Historically, we've always dipped sheep. In Switzerland, they tend to keep their flocks small enough that they don't need to dip them. There's a much lower risk of disease transfer. So in the UK, historically, the dipping process has meant that there have been nasty chemicals in the wool, which have to be processed out. There is a combing exercise, which is traditional with any wool product, sorting it out in such a way that it can be turned into cotton, fibre, whatever it is. But there is another issue with sheep's wool in that it can settle, and some of the products that are on the market are sheep's wool on its own. Others are sheep's wool with plastic fibre that's built into the material so that it maintains the loft, the thickness of the insulation, to keep it the same thickness as it was when it was manufactured. And that enables the insulation to keep on doing its job when it's in an attic, for example.
Number 5 is cellular glass.
Okay, so we probably know this one as foam glass, which is one of the proprietary names. Foam glass is used in places where people can afford it. It has special characteristics, which are rot resistance, fire resistance, animal resistance, rodent resistance. There's a lot of interesting good characteristics. It's got vapor resistance, it's got fire resistance, it's got conductivity, and it also has decrement delay characteristics, the radiant heat resistance. And the first time I discovered this was on the British Library when we were doing roofing, where this thermal insulation material was being applied to concrete slabs. Now, concrete would normally take the heat out of asphalt if you were laying it direct on the concrete. The foam glass was actually stopping that heat from escaping from the asphalt, and instead of going into the concrete, it was going into the insulation. So the insulation was keeping the asphalt warm, and the asphalt was floating down the slopes. So it had to be pushed back up the slopes by the men who knew how to lay asphalt. Okay, until such time as it started to set. So that was a small complication, which none of us had ever experienced before. But it has strong decrement delay characteristics, so it protects you from the solar gains. And it's a very good watertight material, vapor-tight material. So it's ideal in roof construction, ideal in gutter construction, ideal in foundation construction. But there have been some examples where I've actually had a sample in my hand which was fully saturated. Now, for that to happen, it had to be frost damaged. Moisture gets in by frost damaging the outer layer, then the next layer, then the next layer, and then the next layer. This is layers of bubbles. So it gradually works its way through. And that should never, ever happen because the insulation should never be allowed to get wet. And the thing is that you should always wrap it up in a waterproof membrane. If you do anything else, you're in trouble. In most constructions, you'd use it in a flood coat of bitumen so that it's fully encased. And you'd flood coat the surface that you're applying it to, put the board into the insulation, squeeze it into a corner. The bitumen would ooze out through the joints, up onto the surface, squeegee the top surface, and it's a nice waterproof construction. Or in the basement, you would wrap it up in a waterproof membrane and apply it in situ. If you follow the manufacturer's recommendations, you should never have a problem.
And how does this one compare in terms of cost?
Well, sadly, it's a very good material. It's incredibly versatile, but it's a very expensive material. And I would always say use it where it's needed in wet conditions. That's the ideal way to use it. If you can afford to use it in many other places, sometimes you may want to use it in a roof construction where you need the solar protection. But otherwise, where you need it, damp places.
Halfway through our list, and at number 6, we have dense wood fibre. Tell me about this one, Brian.
Well, I think this is one of those kind of magic materials that it's got a lot of interesting properties that apply to many different requirements. Dense wood fibre is one of those materials which comes in two forms. It's a soft material, or it's a dense, rigid material. So it's pretty versatile. And sometimes it's supplied with a rigid face and a soft face. So there's some very special characteristics which can be applied. The important thing is this is a material that's new to the UK market. It's been around in Europe for quite some time. They know how to use it. It's been tried and tested. We have no idea how to use it. So there are people like Natural Building Technologies have been promoting it for quite some time, and a lot of the other manufacturers are beginning to bring it into the UK market. It has moisture management characteristics, which we talked about earlier with cellulose fibre, with the cellulose flake, but this comes in a rigid or soft material. It has acoustic performance, it has conductivity performance, and it's also has these moisture management characteristics, the hygroscopicity characteristic, which allows the moisture to be absorbed into the fibre, allowing the insulation to continue to do its job when conditions are moist. So it's used as an internal lining, an external lining, used on timber construction, on masonry construction. It's used in roofs, it's used in walls, in floors. It can be used as an acoustic underlay. It's an incredibly versatile material. And it's manufactured in two different ways, either a wet process or a dry process. The wet process, inevitably, there's a drying action that needs to be carried out, and so there's a lot more energy goes into the production of the material. The drier process, a lot less energy goes in, but they are very clever materials. If you wrap your building up in dense wood fibre, you can forget about fireworks. You won't hear them anymore. These are very good materials. They have to be installed properly. They have to be made airtight joint construction, and overlapping boards is one way of achieving that. You can use them for external insulation with or without render, weatherboarding, timber frame, all kinds of other materials on the outside. You can use them as an internal dry lining. You can use them on solid wall construction, in cavity wall construction, not in the cavity, on the inside face or the outside face. You can use them for retrofitting old properties which need to continue to breathe. The one thing that we are putting ourselves at risk at is using plastic insulation in old buildings. The two are completely incompatible. Dense wood fibre as an internal lining with a soft surface on one face can apply itself and touch the inside face of the wall, no matter how knobbly that wall is, and make sure that any moisture coming in from the outside can transfer to the inside and evaporate inwards should it need to. If conditions demand that, then it can happen. If you've got any kind of cavity between the insulation and the inside face of the external solid wall, you've got a risk that the moisture can't jump across that cavity and can't escape inwardly when it needs to.
You mentioned retrofit in that, which I guess at the end it might be interesting to look at the two, new build and retrofit, and how all these materials fit into it. But the next one that we're coming to, I suppose, has a use in retrofit. It's aerogel.
Yeah, aerogel is an interesting one. It was invented by NASA. Guys who were bored because there weren't many space flights. What should we do? Oh, let's see if we can get some water out of jam and leave the jam behind. Okay, interesting, weird and wonderful places the NASA guys get to. And then somebody came up to them and said, okay, that thing you did with the jam, can you do it to make a thermal insulation material for the spacecrafts that are going to go and come back and go and come back. They'll have a ceramic surface to protect them, but we need some thermal insulation. And it needs to be thin. So what can you do for us? So they created aerogels. And aerogels are significantly better performance than the foamed plastics. It's microscopic bubbles inside a matrix, and they are very high performance. They add into them some fibres to kind of hold that material together, and then they usually bond them to a board, and that board could be a dry lining, like a plasterboard. And these become very important when you get to things like window and door jambs, where there's a very high risk of conductivity, thermal bridging across between the stone or the brick outer face, bypassing the window and coming in through the jamb. So there's a high risk of cold, condensation, mould in that position. So if you've got a very thin insulation which can go around the lining of the jamb, you can deal with the risk. And so that's a very popular material used with other materials for dry lining the rest of the walls.
I'm imagining expensive and probably not great for the environment as well.
It's clay-based, so it's not that bad in that respect, but there's probably an awful lot of energy gone into making it. It is an expensive material, and because the vast majority of it was coming from America, then when the Americans discovered thermal insulation and then they discovered aerogels, it became expensive. So yeah, it's an expensive one, and use it in the special places you need it, in those condensation mould risk problems.
Number 8, we've put calcium silicate.
Okay, calcium silicate has come from places like Germany, where it's been particularly invented for historic buildings. And they tried lots of different recipes to find the optimum material for working with historic buildings. And they've been used as an internal dry lining, thermal insulating material. So it effectively makes its own lining board. And sometimes that would be skimmed with a material for decorative purposes. But it's an incredibly lightweight material. It's probably a waste product from some process. Don't really know the details of that. But a very good high-performance material with moisture transport characteristics, which mean you can use it on the inside face of a solid external wall, and any moisture that gets in from the outside face works its way through the brickwork and comes to the inside face. It has a way out internally through this moisture transport thermal insulation material. And you'd bond it to the inside face of the external wall to make sure that it's in contact, there's no cavity, no risk of the moisture not being able to jump across.
We're getting close to the end of our list here. At number 9, we've got vacuum insulating panels, which sound very technical.
They are a bit, yes. What it is a steel cassette, which is a hollow steel panel. They then suck the air out of it. And as we all know, vacuum is a very good thermally insulating material. It's used in flasks for keeping drinks hot or cold. In this case, as you can imagine, if you've got a vacuum panel, if you've got to kind of fit it into a construction, and the construction's all kind of different sizes and shapes, you're going to have to start cutting things. You can't cut vacuum insulated panels. They leak, they hiss and blow, and they lose their properties. So they're ideal in a modular design, but if we're kind of using them in a retrofit situation, you just don't have that. So you'd have to use them in combination with another material. And the best combination that I can come up with so far is either an aerogel side by side or a dense wood fibre, but it's about getting the right thicknesses to make sure that you've got kind of level surfaces for following trades.
And does this one put itself at risk of failing in certain circumstances, or is that what you're saying about the modular design, for example, that it's much safer then?
Yeah, if you use the modular design and everything is made to suit, or bespoke, it can be bespoke or modular. So bespoke would be purpose-made to a specific size. The risk is somebody sticks a nail through it, somebody drills a hole to fix something to it. So you've got to put them in places where no one's going to likely to do that in the future.
And at number 10, insulating render. We've made it.
Yeah. Okay, so insulating render, it's a fairly new material in the market, and I'm not talking about insulation plus render on the outside of a wall. I'm talking about a render which is insulating throughout its thickness. So it's a material which is clay and other ingredient-based material, and it's had special ingredients added like a cork aggregate, which is just part of the mix. It's applied as a render, it's applied as a plaster, it's applied as a screed, and it will accommodate all the lumps and bumps of an existing surface, including chasing out for conduits and everything else. Pretty versatile, and applied by specialists or possibly applied by a self-builder. You would need to investigate that one a little bit more to find out. And because it's a through and through thermal insulating material, you don't have the risks of condensation. You don't have to have vapor barriers and other special membranes applied to the construction. It's just applied like a render and off you go. Fairly thick, probably talking about 100 millimetres and maybe more, can be applied relatively thick. And occasionally, if the walls are really lumpy and bumpy, you might have to apply a first coat and then apply a second to build up the thicknesses that you need to achieve the U values that you require.
Well, Brian, we've made it through the list. I'm probably going to ask a very stupid thing here, but if we want to try and be environmentally friendly, are there any that we should pick out of here, or is this just swings and roundabouts?
Don't try to be green and friendly for the wrong reasons. Choose the right material for the right properties of the right application. Once you've made those decisions, then you're going to have a solid, sound building that you've invested well in, and you're not going to have any risks later on.
And my final question is about retrofit. Is it, again, a similar approach?
Yes, you've got to pick the right material for the job. So it's got to be hygroscopic. It's got to be moisture transport capability, and it's got to be compatible with the existing building fabric.
Brian, thank you very much.
Okay, pleasure. My pleasure. Thank you.
Lots to take in, which is why we have our show notes. We've got a summary of each of the insulation types that we've mentioned and photos of them as well. Links to Brian and Green Building Encyclopedia, all at houseplanninghelp.com/94. And that's a place if you want to leave a comment at the bottom of the show notes, or a question perhaps. My call to action today is please write an honest review of the podcast if you haven't done so already. It just helps other people locate this podcast because it bumps us up in the iTunes store. This one is from Purple Orangutan in the UK. We're planning on improving the energy efficiency of our house, and this podcast is brilliant to gen up on all the latest tech and techniques. Really interesting interviews with real people who have built or retrofit their homes. Great to have a British podcast with global reach. Oh, that sounds good, doesn't it? Next time we are heading to Canada, and we're also in for a history lesson. I like to mix things up, you probably know that. What is the Saskatchewan Conservation House, and why was it so groundbreaking? We hear from an amazing man, a pioneer in fact, Harold Orr. That's next time. The House Planning Help podcast is produced by Regen Media, content that matters.